All right, let's get back to our examples here. Now, we've done two. Okay, they illustrated a couple of points here. Sometimes you can have polar bonds and the molecule's polar. Sometimes you have polar bonds and the molecule's nonpolar, if it's arranged symmetrically. Let's do another one. Let's do the one I mentioned a little while ago, and this one's going to illustrate something else, something that makes the electron dot notations hard. All right, so the last one I'm going to be able to fit on this board. I don't know how much room you have there, but I'm going to do carbon dioxide next, CO2.
A lot of them.
Or wait, maybe I'm not. Maybe I'm going to do, hold on a second. Yeah, maybe I'm going to do, yeah, I'll do CF4 next. Okay, and you want to skip a little, move it a little bit lower down because, like I said, this one's going to take up a little bit more space because it has 4 atoms to draw, besides the central atom. So you might want to skip it down so you don't run the electron dots into each other. First off, look up the C and F and tell me what kind of electronegativity difference you have between them.
Just 1.4.
1.4? Okay. So 1.4. Oh.
1.44.
1.44. Okay. And that makes, either way, it makes it polar. Okay. We're going to draw carbon, and it helps if you know carbon's making, it helps if you know carbon's making a bond. That I'm going to draw him just with the 4 dots around him. Remember, he undergoes some type of hybridization anyway when he forms a compound. Right, sp2 or sp3 or sp1, whatever. And so I just want to draw them like that. A lot of times when I used to draw electron dot notations, I would draw them like this, putting the first 2 to the right, indicating the s orbital, p1, p2, p3. But it's just as easy, probably easier to draw it like that. Knowing that the same thing is the case. He has 4, he wants 4 electrons to get his octet. Okay? And he's got 4 electrons to share with someone else who happens to need some. I'm going to draw fluorine. I need 4 fluorines. I'm going to draw 4 Fs. You all know what fluorine looks like. You see group 7, he has 7 electron dots, so he would look like that. Now, I asked myself, very simple question, how can I make these both of these guys happy? And, you know, from last year, I think you could all do this one pretty much in your head. It's pretty easy. This guy wants to gain 1 more electron. He's got 4 electrons to be shared. I'm going to put them at every one of those places, right? Everybody would do that, I think? Okay, now, like I said, this is going to be a large one to draw. So I'm going to kind of move him down here just because the board isn't very wide. And I'll put the carbon here. And then my fluorines with their 7 electrons, like that. And there's carbon tetrafluoride. All right. Now, here comes the Vesper Theory. We've got to use it to predict the shape and how that shape is going to actually affect the polarity of the molecule. All right, this shape, I've already kind of hinted at it when we were talking about carbon itself. When we're talking about sp3 hybridization in, say, for example, a diamond, versus the sp2 hybridization that's in, for example, the graphite. Okay? What did I say the shape was? You remember it? What is this shape? 4 things bound around the central atom. Right? Tetrahedral. It's both on the back of that paper you just read, and it's also the same word I use when I talk about diamond. Okay, tetrahedral kind of shape for carbon. Only this time, instead of other carbons being around that carbon, there's other hydrogens, or in this case, other fluorines. All right? Now, in every one of these cases, all right, I'll back up here. I didn't draw it on here, but I could have. We have to look at it like fluorine. Chlorine was pulling this way, pulling that way, pulling that way. Fluorine's pulling that way, pulling that way, pulling that way, pulling that way. Okay? And if I look at this guy, once again, Mr. Schrader could have done this. I don't know if he did. But he could have hung something from the ceiling with 3. Did you ever do that? We had to add up the vertical component of more than just 2 things. All right, but either way, the point is, as hard as this guy's pulling that way, these other 3 add up to be the equivalent of pulling the opposite. So this is a symmetrical molecule. You see why it's symmetrical? It kind of looks like it's exactly the same. It's going to cancel each other out. Okay? It is symmetrical. The angles between these guys are all exactly the same, 109.5. You don't have to know that. All right, but the angles between them are all exactly the same. the things at the end of them, the fluorines at the end of them, are all exactly the same, pulling exactly the same way. And remember, they want to get as far apart as possible. So their shape is going to be, again, I want to use green, their shape is going to be tetrahedral. And since that tetrahedral shape is symmetrical, that makes this guy what? The compound what? Non-polar. Okay? It is not polar because this guy's pulling and it's being canceled out by the three other guys pulling at equal angles away from him. Okay? All right. So far, so good. But things are going to get a little bit more hairy now. All right. First off, I'm going to make it a little bit worse by doing one that may surprise you a little bit. It's not going to necessarily be a symmetrical molecule, but you might think it is. And it's going to involve electrons in pairs instead of actual atoms. That's where the Vesper theory comes in as well. Right? I have to erase this board, though, because like I knew I wouldn't have room to show all these. You guys may be on the back side by now. You may have room to do one more. But we're going to do 3 more. So, all right, ready? Everybody got that? Okay. Let's do NH3. Now, if I draw NH3, I first look up N and H, difference, subtract them. What do I get? 0.6 what? Or what is it?
0.61.
0.61? 0.61, which makes him polar. We had a lot of compounds that were polar. I did not do one that was only nonpolar. Because if I did one that was only nonpolar, what would my answer have to be over there? Nonpolar. All right. I'm going to draw N by himself. Try this one on your own, actually. Just do that guy. See if you can do that one on your own. I'll give you a second to try this guy on your own. At least do an electron dots on your own, if nothing else. Then I'll do it on the board. Because you're going to be doing these on your own in a minute. When I'm done with this 3 more examples. Draw N by himself, draw H by himself, put them together the way you would think they would fit to satisfy the octet rule, not creating or destroying electrons, giving everybody an octet where you can. And then see if you can predict the shape. I would hope you all do that for the 2 separately, right? And you have a 3. There's 3 actually H's. And I would hope you put them together like this. It doesn't really matter where you put the H's. If you wanted to put them like this, because it kind of looks that way anyway, that would be fine. But if the H's were in different spots, it doesn't matter. You all good with that? All right. What shape is that? Well, here's the problem with this. The obvious answer is not correct. When I drew a little while ago boron trichloride, don't have to draw this, just watch. This is already drawn. You already have this guy on there, right? When I drew this guy a little while ago, I asked you how many things are bound around the central atom, which is the big question. And the answer you said was 3, and that's correct. 3 things get as far apart when they are triangular planar, like this guy. This time, I'm asking you how many things are bound around a central atom, and what do you tell me? No. You say 3, but it's not correct. It's not the obvious answer. The Vesper theory, if you read that article, the Vesper theory says electron pairs act. They repel, just like these electron bonds here, these that are actually bound to some other atom. They repel as well. This electron pair, that's why it's called the valence shell electron pair repulsion theory. All right, these electrons actually repel. It's like having 4 things bound around that guy. But of the 4 things that are bound, you say, well, okay, so my answer is tetrahedron, right? No. Of the 4 things that are bound, 1 of them are just electrons. So it really looks like this. What is that? Look on the back of your sheet if you don't know. You probably don't know. Triangular what? Pyramidal, right. Triangular pyramidal or trigonal pyramidal. Okay, good. Triangular pyramidal. like a pyramid. Kind of looks like a pyramid, doesn't it? And here's the difference, people. This is where the Vesper theory comes into play. The electron that are up here in an orbital, okay, the electron pairs that are up here, they repel just like if there was an atom there. But there's not an atom there. If there was an atom there, I'd call it tetrahedron. There's not, so I call it pyramid. Looks like a pyramid. Okay? Is this symmetrical? No. It kind of looks symmetrical if I hold it like this, but it's clearly missing its top. Okay? So it's like at Mardi Gras. It's got some beads. It's missing its top. You guys know about Mardi Gras? Seriously? You guys shouldn't wear beads, by the way, when you do that like Mardi Gras stuff here. It's not a good idea. But anyway, yeah, it's missing the top, so it doesn't have anybody pulling that way. These guys over here, all right, are kind of symmetrical. They look this way, but if you look at it this way, it's clearly not, which means the molecule is polar. It is still polar. There is a difference in charge because, you know, of this guy's pulling, nitrogen's pulling this way, and this way, and this way, but there's nobody pulling opposite that. Right? By the way, turns out the H is less nitrogenated than N anyway, so that would make it kind of weird anyway. But okay, so you get the idea. It's not a symmetrical molecule. You are going to have a slightly negative versus a slightly positive charge. This side is pulling that way, and that way, and that way. All right? So you're going to have slightly, the H's are going to be slightly positive, and the top of this pyramid is going to be slightly negative. Okay? Polar means not completely, it's not an ionic charge, but it is going to be positive or negative. All right. Now let me erase this guy. All right. Couple more to do. This next one. Now I want to do this guy. Watch this one. One of our most famous compounds we've been talking about for a very long time. I know I've asked you to do this guy's electron dot notation in the past. You've all done it in Chem 1. Try this one on your own. What's the electronegativity difference, first of all? What is it? 1.1. Is it 1.8? 1.17? Okay. So 1.17 polar. Makes it polar. Draw him. See if you can get him right. Draw separately the H, separately the O, put them together, make an octet, predict the shape, and predict the charge. And this one, I'm hoping you might get right. I was not expecting you to get triangular pyramidal correct. But now you know what to watch out for. Now you know those electron pairs count. So, see if you can figure it out. Hope you all wrote this. All right? And it doesn't matter how you draw that. I mean, if you wrote it like this, I would not take off points. As long as you realize that ain't the shape. That is not the shape. What is the shape? It is not linear. I bet some people put down linear. It is not. How many things are bound around the central O? No.
Wait, no, that's not right.
4. 4 things are bound around the central O. Two of those things happen to be electron pairs. But they act just like atoms, and they're going to push away. So that means the shape is what? Bent. Shape is bent. Let me show you again with this. Watch. Here's your actual shape, if you're including all the electron pairs. Pull 2 of those off because they're not atoms, and that's what you got. Turns out the actual angle between these is not still what it would be as if it were a tetrahedron. all right, because the electron pairs repel differently. But that's not important. You will have to know that possibly in college, all right? But you are going to have a different repulsion by the electron pairs than you would have by an atom that was there. So these numbers are 109.5, and water's actual angle between it is not, but it's similar. It's very close, and it is bent. And that makes the charge, or that makes this guy what? Is bent symmetrical? No. So that means he's polar. Got it? Last one. I told you I was doing 3. It's the last one. This is going to be a little bit more difficult, not because of the final result. This is what I'm going to make, carbon dioxide. We already know what the answer is going to be. It's going to be more difficult because of the electron dot notation. Okay, watch. And you will have to deal with this. We had to deal with it very briefly in Chem 1 as well. Didn't do a lot with it, but we are going to have to see it again. CO2. The difference between C and O is what? Point what? 8.1 or 9.1? 8.1. That makes it polar. I draw my carbon. I draw my oxygen. Oops, sorry. That's pretty bad. Okay, and I have 2 O's to put in there. So what am I going to get from making those 2 guys together? Ah, here's your problem. You may remember me doing this one in Chem 1. You may not. And he does have a trick to him. See if anybody can remember what that trick is. You can't do what I think you want to do. It would be nice if we could just do this. Kind of catchy. All right, it'd be nice if we could just do that. There's my carbon dioxide. Well, what's wrong with that? Some people are probably saying, that's what I got. What's wrong with that? Anybody know? Yeah, I got a lot of extra electrons here. 2 times 6 is 12. 13, 14, 15, 16 electrons is the total amount of electrons I have on the left side. Here I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, I believe, if I count it correctly. But either way, it's way more than I should have. All right, well, I just erase a couple. If I just erase a couple, the problem with that is I no longer, I'll erase 2 here, I'll erase 2 here, I'll erase 2 here. I no longer have an octet for everybody, right? That's a problem. So what do I do? Anybody remember from last year what you have to do in this kind of case? Nobody? Somebody remembers. Hannah remembers.
This can't oxygen have double bonds.
That's right, double bonds. Oops, what did I do there? I was double bonds, absolutely. Turns out that you're going to end up sharing 2 pairs of electrons between these guys. That we want 2 pairs shared there and 2 pairs shared between the other ones. So it kind of looks like this. Carbon's in the middle, and you'll share 2 pairs of electrons between those guys and 2 pairs of electrons between those guys. Now let me show you why that helps us and makes sense. Okay? It also explains why I've got these weird bendy bonds in here. Turns out, by doing it that way, first of all, let me show you how I've managed the 2 things I need to always keep in mind. All right? 2 things I want to always keep in mind when I'm doing electron dot notations. 1, I can't create or destroy electrons. That's inviolable. You cannot violate that law. All right? 2, 4, 6, 8, 10, 12, 14, 16. That's how many I said we had before. So 16 on that side and 16 on that side. We're good. Second rule, it can be violated. I mean, you want to give everybody an octet where humanly possible. It's not always possible. For example, hydrogen, boron. We already did 2 examples where you don't get an actual octet. But where possible, you want to give it an octet. And that means you may have to make double or even triple bonds in order for them to share more than 1 pair of electrons at the same time. Look what happens. Does carbon have an octet? Sure. 2, 4, 6, 8. It's sharing 8 electrons. Does this oxygen have an octet? Yeah. Let me show you. I'll use a different color. I'll use orange. He's got 2, 4, 6, 8, and this oxygen's got 2, 4, 6, 8. So they all managed to get their octets. I didn't create or destroy electrons, and it ended up with double bonds, and that's what's shown by these double bonds. 2 pair here, 2 pair here, a single line. A lot of times you'll see drawn. And as we go on with Chem 2, as we go on with the AP and the organic we're going to do, you're going to find that I will not draw methane or carbon tetrafluoride. I'm not going to draw it like this. It's just a pain in the neck. That's a pain to draw that, right? I'm just going to draw like that. I'm going to use those for the bonds. That is an H there, okay? So instead of putting 2 electrons, I often replace that with a bond. So that line between here indicates a pair of electrons. Well, of course, 2 lines in between here indicate 2 pairs of electrons, and that would also be drawn like this. You can draw it like that as well. Now, this actually, for the Vesper theory, is a pretty easy one. The hard part of this guy was getting the double bonds. This is actually a fairly easy guy, isn't he? He's pulling that way. As I said, I used him to start me off here. He's pulling that way. So it's pretty obvious if this guy's pulling this way. Right. Okay. Interesting. There you go. And this guy's pulling that way. They're going to cancel each other out. Okay? Which means that the molecule itself, first of all, what's the shape? What's the shape? This is linear. This is linear. Which kind of also gives me a problem I often get with people. They're going to see linear here, and they're going to say, okay, linear is people who think very, well, inside the box, let's just say. They want to memorize stuff. This is how Nikki does. I always used to yell at Nikki and kept one. I know you don't. I'm just saying. People who want to memorize are going to say, but you said whenever it's linear, it's symmetrical, and therefore it's nonpolar. Okay, which it is in this case. But that's not what I said. I didn't say every time it's linear, it's symmetrical. Let's go back to the first one I did, HBr. What's the shape of HBr? Linear. Is it symmetrical? No. So it depends. If you got somebody on your side pulling, absolutely. All right. Your job now, I'm going to pass these out. I'm going to have you fill in parts of this today. I'm going to shut the video off. And then we'll finish the rest tomorrow as part of the lab. We'll make the models.